The topic that we are presenting are the periodic table and valence electrons. We will start by explaining what they are and presenting the history, scientists involved, natural phenomenons that are involved or related, how they're related to each other, and current research trends that explain what scientists are doing today with these topics.
In a video store, the latest movies are usually placed on the shelves in alphabetical order. The manager has to choose a set of categories and then place each movie in the most appropriate location.
Scientists face a similar problem when they look for a logical way to organize elements. The placement of elements on the table reveals the link between the atomic structure of the elements and their properties.
An organized table of the elements is one of the most useful tools in chemistry. Let's talk about our current updated periodic table today.
In the modern periodic table, elements are arranged by increasing atomic numbers, which is number of protons. There are 7 rows or periods in the table. There are 32 columns or groups in the periodic table.
Each row in the periodic table is a period. The number of elements per period varies because the number of available orbital increases from energy level to energy level.
Each column on the periodic table is called a group. The elements within a group have similar properties. This pattern of repeating properties is the periodic law.
There are 4 pieces of information for each element, which are the name of the element, its symbol, its atomic number, and its atomic mass. Atomic mass is a value that depends on the distribution of an element's isotopes in nature and the masses of those isotopes.
In the periodic table, there are certain classes of elements, which are metals, nonmetals, and metalloids. In the current periodic table, metals are located on the left, nonmetals are on the right, and metalloids are in between.
The majority of the elements on the periodic table are classified as metals. Metals are elements that are good conductors of electric currents and heat. The metals in group 3 through 12 are called transition metals.
Transition metals are metals that form a bridge between the elements on the left and right sides of the table. One property of many transition metals is their ability to form compounds with distinctive colors.
Nonmetals are elements that are poor conductors of heat and electric current. In fact, all gases in the periodic table are nonmetals.
Metalloids are elements with properties that fall between those of metals and nonmetals. Pure silicon and germanium are good insulators at low temperatures and good conductors at high temperatures.
That was just a little overview of what the periodic table of elements really consists of. Let's look at the history of the periodic table, and then we'll talk a bit about valence electrons.
In 1864, English chemist John Newlands noticed that if the elements were arranged in order of atomic weight, there was a periodic similarity every 7th element.
In 1868, Lothar Meyer compiled a periodic table of 56 elements based on a regularly repeating pattern of physical properties such as molar volume.
In 1862, French geologist
Alexandre-Émile Béguer de Chancourtois
plotted the atomic weight of elements on paper tape and wound them spiral-like around a cylinder. The design puts similar elements into corresponding points above and below one another.
In 1869, Russian chemist Dmitry Mendeleev produced a periodic table based on atomic weights, but arranged periodically. It was based off a card game. He also published a paper entitled On the Relationship of the Properties of Elements to Their Atomic Weights.
Mendeleev really be out there finding elements while playing cards, huh?
Mendeleev arranged the elements into rows in order of increasing mass so that elements with similar properties were in the same column.
although he couldn't complete it because the rest of the elements weren't found.
What would you say if you saw nobelium and silicon after a long time? Long time no see!
Oh my gosh.
A close match between Mendeleev's predictions and the actual properties of new elements showed how useful his periodic table could be.
Alright, let's get back to the timeline. In 1894, William Ramsay discovered the noble gases and realized that they represented a new group in the periodic table.
In 1913, Henry Moseley determined the atomic number of each of the known elements.
And in 1944, Glenn Seaborg proposed an actinide hypothesis and published his version of the table in 1945.
Now, what would you do if a good chemist starts dying after hearing your lame chemistry jokes? You bury him.
Let's get started on the valence electrons, but first let's describe what they are and how they relate to the periodic table.
Valence electrons are any of the fundamental negatively charged particles in the outermost region of atoms enters into the formation of chemical bonds. Whatever the type of chemical bond, ionic, covalent, metallic, between atoms, changes in the atomic structure are restricted to the outermost or valence electrons.
They are more weakly attracted to the positive atomic nucleus than they are to the inner electrons, and thus can be shared or transferred in the process of bonding into adjacent atoms.
Valence electrons are also involved in the conduction of electric current in metals and semiconductors.
Valence electrons are related to the periodic table in the sense that they are determined where certain elements are placed. They also relate to where the positions of the elements in terms of the groups and the periods. Let's move to some history.
In 1902, while trying to find a way to explain the periodic tables to his students, the chemist Gilbert Newton Lewis discovered that the chemistry of the main group elements could be explained using a model in which electrons arranged around atoms are conceived as occupying the faces of concentric cubes.
By 1916, Lewis realized that there was another way that atoms can combine to achieve an octet of valence electrons. They can share electrons and form a covalent bond.
All right, let's talk about the natural phenomena that are involved with both these topics, and then we'll get into the current research trends.
The natural phenomena involved with the periodic table is that some of the elements that have been found were found because of the predictions. Scientists predicted these elements using the properties surrounded by the other elements, and then they found newer elements.
The natural phenomenon that is involved with the valence electrons is that the elements with the respective number of valence electrons have similar to those of the same number. In this way, we can see that the valence electrons are also a key factor in determining or predicting the positions of newer elements.
Some current research trends that are related to the elements in the table are recently that scientists found 4 new elements that were synthetically created in labs. Researchers realized that the end to the periodic table is unknown, but there's a limit for humans to create new elements.
A research trend for valence electrons involves their role in quantum computing. Quantum computing is a potential solution to the limits of computers based on silicon microprocessors. There are some computational problems that require more computing power than we have in the world today. Quantum computers use quantum mechanical phenomena to exponentially increase the number of bits. Scientists are creating special atoms called Rydberg atoms, which have a singular outer valence electron that can be excited to very high quantum states. The excited valence electron in a Rydberg atom can travel as far as microns from the nucleus. That's millions of times further than they usually are. This allows Rydberg atoms to interact with nearby atoms and to be controlled by light. These characteristics can help scientists construct quantum computers.
Can you see it?
Can't believe it really existed.
An element of surprise.
And that's all,
Oh my gosh!
Okay, goodbye.
No, that's all, folks!
Did you just start that?
Oh my god!